Hello, everyone. Today, we're going to do this thing in two parts. First, we're going to start with a lecture on spring physics, which we'll get to in just half a moment. And then, after that, we're going to jump into Xcode and actually implement a little spring animation library from scratch. There's going to be a part 2 where we make that library extra shiny, but we'll actually get a working thing here today. So let's go. So now let's discuss the physics behind spring animations, and don't go screaming towards the hills. Let me attempt to explain it in as simple as terms as I can. So here we have some intended animation. We have our current position over here on the left, the outlined circle, and we have its target position here on the right-hand side. We would like to animate from our current to our target position. When thinking in terms of springs, which are modeled from real-world spring physics, we will change this up a little bit and instead think of the target as some magical point of equilibrium, the position that our object considers its home base, towards which it would like to return as swiftly as it possibly can. And we will consider the fact that our object is not at its point of equilibrium as its displacement. Our object has been displaced from its target equilibrium state by some amount. With our simple example here, we can consider our position along the x-axis. So if our object is currently at 50 units and its point of equilibrium is at 150 units, we can take the difference here and realize that our object is displaced negative 100 units. So this is our first term, our displacement, how far away we've moved from our intended target equilibrium point. And if you can imagine us holding this sphere here in stasis as it's been displaced from its peaceful home, you might imagine that there is some force subtly tugging on it, pulling it back towards equilibrium. And indeed there is. And there's a fancy physics term known as Hooke's law, which determines exactly what that force is and how it's calculated. And it's a very simple calculation. The spring force is a product of our displacement along with some stiffness value, which is to be considered the strength of the spring, how much that spring wants to pull its object back into equilibrium. And notice here we're negating the displacement because the spring force acts against displacement. There's this force pulling it back home. We've dragged our object off to the left, and these spring forces are tugging it, pushing it back towards equilibrium. And we can adjust this spring force in multiple ways. One would be by adjusting the stiffness. So we could make our spring less stiff, and that would reduce the spring force. We could make it truly meager, barely a spring at all maybe. Now it's just attached by a rubber rope. Or we could have a very insistent, hearty spring that really wants to pull its object back into equilibrium. But that is not the only factor here. Stiffness is only one element, the other is the displacement. So if we were less displaced, if our object was closer to equilibrium, that would also result in a decrease in the spring force, because the factor of displacement is going to be lower, even with the same stiffness. It may have been the same stiffness as before here, but we are less displaced, thus there will be less of a force. And of course, if our object is in perfect equilibrium, if it is in its home position, there will be no spring force acting on it. It will be resting peacefully at home. Despite there being a stiffness to the spring, there is no displacement, and so 0 times anything will negate the spring force entirely. Alright, so we've discussed these two terms with regards to spring physics, displacement, and then this restorative spring force, which seeks to undo the displacement, to negate the displacement. So let's get rid of some of these notes here. So along with displacement and the spring force, there is this other notion that we must consider. Once we release our object, this spring force will have an effect on our object. It will cause it to move. It will cause it to accelerate. And that will give it a velocity, represented here by this blue line. And as our ball accelerates towards its point of equilibrium, it will be less displaced, which will reduce the spring force. So our ball will continue to accelerate in this situation, just at a lower rate than it did originally. The fastest acceleration will actually happen when it's the furthest away from its home base. So we'll very quickly reach this middle point, and then acceleration will continue, but at a slower clip. And all things will continue until we will actually eventually overshoot the point of equilibrium, because we've been traveling so quickly towards the right here. And once we do overshoot our point of equilibrium, we will now be displaced towards the right. Therefore, the spring force will begin to act against the current direction our ball is traveling in, and the ball will begin to decelerate until it finally reaches its stopping point at the exact opposite location towards where it originally began. In this, of course, idealized scenario where the only force acting upon our ball here is the spring force, it will continue to oscillate essentially back and forth forever, because now we're sort of exactly as we started, except in a reflected state. So we will travel back in the other direction. As we approach, the spring force will decrease, so our acceleration will decrease, but we'll still be accelerating until we surpass equilibrium, and then we start to get slowed down by the spring force in the other direction until we stop where we started, and will continue forever. And that's cool and all, but this would lead to some really frustrating user interface animations if this is how our phones worked. If everything was just sort of oscillating infinitely back and forth on our screen all the time, I don't think iPhones would have been a successful product. They would have caused people to throw up. So because of this, we want to steal some more concepts from real-world physics and introduce some notion of resistance to our system. In the real world, springs will not oscillate infinitely because those objects in this relationship are going to be suspended in some substrate, some material, be it air or water or molasses. And that will cause some amount of friction to the system. It will add some resistance, and it will eventually bring these oscillations to a halt. And luckily for us, that makes the springs feel better and look better and not just kind of wobble around infinitely. So let us introduce another force. As our ball here is moving through space with some velocity, pulled or pushed, however you wish to conceive it, by the spring force back toward equilibrium, we can imagine that instead of being in this black void of space, we are in some sort of thick black liquid, which will seek to actually slow the velocity of our ball here. And there will be this contravening damping force acting against our velocity. This other key term of spring physics is damping, and it will lead to this damping force, which is a product, just as the spring force was a product of the stiffness of the spring multiplied by its displacement. The damping force is the product of the velocity, so how quickly our ball is moving, along with this other knob we have on our spring system known as damping. And we can think of this as the amount of resistance in our system, maybe the viscosity of the liquid our springy ball is suspended in. And just like stiffness, this can either be extreme or quite subtle. It's a knob to play with, and it will affect the way our animation eventually looks. And also, just like the spring force, when our ball was at its point of equilibrium, no matter how stiff the spring was, it could be the stiffest spring in the world, but because we were not displaced, the spring force was zero. That zero eradicated the entire force. Similarly, because the damping force is a product of both velocity and this damping factor, if velocity is zero, if we are at our starting position and we have no velocity, well then similarly we have no damping force. If a ball is sitting in some very viscous molasses and it's not moving, well the ball is already static. It's not going to be affected by the thick liquid it is submerged in. If it were moving, that liquid would serve to slow it down, applying said damping force to it, but it's not going to start moving it if it's not already moving. But once we do begin moving, pulled by our spring force, well now we'll have some velocity, and therefore, as long as we have some amount of damping, the damping force will come into play. And this is now going to be a negative force along the x-axis, because it's always going to be opposite our velocity, attempting to counteract our velocity. And this is very interesting because we now have two forces acting upon our ball. We have the spring force pushing it toward equilibrium, and the damping force pushing against the velocity. And so to figure out exactly the true resulting force that's acting upon our ball, influencing its velocity, we'll have to add together these two forces. And so if we subtract the negative damping force from our positive spring force, we'll end up with this resultant force, which will actually determine the acceleration of our ball at this point in space. And it's interesting because this is always going to be in flux. Here, we're still quite displaced from equilibrium, so the spring force is quite significant, and we're not moving very quickly, so the damping force is relatively small, and therefore we're still going to be accelerating. But as we continue to accelerate, this is doing two things. It's bringing us closer to our equilibrium, which is reducing our displacement, thereby reducing the spring force, and it's simultaneously increasing our velocity, which is increasing the damping force, which means now when we sum these two forces together, we're going to get a negative force. The damping force outstrips the spring force, and now we will begin decelerating. We will not begin reversing quite yet, but we will begin decelerating on our approach. And as we get even closer, our velocity is smaller, therefore the damping force is smaller, but we're also still closer, therefore our spring force is smaller. And so there's still this slowing force. And if the stiffness of the spring and the damping, these two knobs on our spring system, are calibrated just so, there is a possibility that we will come to a perfect stop precisely at the point of equilibrium, and thereby remain there. If that happens, if we sort of perfectly roll to a stop here, guided by those spring and damping forces without overshooting, that is known as a critically damped spring. If you've ever seen the word critical damping anywhere in the iOS docs, that's kind of what that means. It's a physics term about the relationship of the damping factor and the stiffness factor of our spring system. Basically, we reach equilibrium as quickly as possible without overshooting. A real-world metaphor would be one of those auto-shutting doors that do not slam the door, but bring it in swiftly and then close it without a sound. There's another classification of spring systems that's worth our attention, and that's where the damping knob is turned down a bit more, where it's not strong enough to actually bring us to a complete stop, and we will overshoot slightly. And that's known as an underdamped system. And that's where there will be a slight bit of bounce. We'll overshoot, and then we will return gently to equilibrium, or perhaps oscillate very subtly around the equilibrium point. And you'll see both of these systems used. There's also an overdamped system where the damping force is way too high, and things just end up looking really awkward, so we're not even really going to worry about that. That just ends up looking wacky. So we're mostly going to see critically damped systems. This is actually the default when you use an animation block, the default spring animation in SwiftUI. And then if you use one of the other settings like bouncy, or you mess around with those bounciness properties, it's going to be slightly underdamped. So yeah, that basically does it for our physics lesson. I hope that was interesting. I've certainly implemented animation libraries before and just kind of treated all of this math as a strange incantation that was completely opaque to me. But now I feel really good about having done just a little bit of research and understanding the underlying principles here, which, to be honest, are not very complicated. So now I think we're about ready to actually code this thing from scratch. And when we get to the mathematical physics portion of the code, I hope you keep these little animated diagrams in mind. And I hope that the few mathematical incantations we must write are now mostly demystified, and you have a few light bulbs flashing in your head. Okay, onward to code. All right, so here we are in the code. Let's get rid of all of this nonsense and make something new. We're going to make a circles view, actually. We're going to make a new view up here, circles view, and this will look sort of like what we just had in the previous section. We'll have a body. We're going to make that a Z stack, and we'll put a few circles in here. We'll start with just one, filling it with a tertiary style, making it 100 by 100. Lovely. We're going to duplicate it, and we're going to offset them, one by -200 and the other by +200. So these will be our two target states. And then we're going to have the circle that we're going to animate, and instead of filling this, I will stroke it with the primary color and a line width of 8. And I suppose I'll fill it, make it black inside. And then instead of having a fixed offset here, we're going to accept the offset from above. So there's that offset. I will collapse these onto single lines so we can see more. And then we'll make the offset a state in here. Offset is a double, and we'll start it at 200. Offset, offset. And then on a tap gesture, we will essentially multiply the offset by -1. And this will toggle the circle between the two positions. And since we have not yet animated, and since we have not implemented our own spring animation yet, let's just use the default one for now. So we'll use a spring animation when the offset changes. And there we go. We can see this critically damped spring animation that shoots towards its target and then slows to a perfect stop. And if I make this a bit slower, giving it a duration of 1, we can really see that damping effect as it comes to a perfect stop at its target without overshooting. Similarly, if I use the bouncy preset, we'll see how it's now an underdamped spring that slightly overshoots its target before returning to perfect equilibrium. But the point of this whole video is not to use the built-in animation, it's to do it ourselves. So I'm going to go back to the spring animation here. I'm going to make an H stack, and then scrolling down, I will copy the circles view. So we'll have two of them. Let's add some spacing between so it doesn't look horrifying. And now the one on the right jumps uncomfortably between the two positions, and the other one is spring animated. It is going to be our goal to have the value on the right look essentially the same as the value on the left. And let's think how we can possibly do this. Well, right now, our offset is just jumping between these 2 points of -200 and 200. Yet clearly, on the left-hand side, the circle is not just jumping, but elegantly, smoothly springing towards its new destination. So clearly, internally, somewhere in the SwiftUI runtime, there is not merely the numbers 200 and -200. Somewhere in that runtime, SwiftUI is simulating spring physics, and it's storing the actual position of the circle rendered on the screen, somewhere between 200 and negative 200. So we need a way of doing this ourselves, of simulating the spring physics and updating this offset not just once to its target location, but many times. And one question might be, how many times should that be? Well, in order for things to look nice, and in order to not perform any redundant computation, we would like to update the position on the screen every time the screen renders. We would like to process the next step in the physics animation each time the screen refreshes. The precise refresh rate, that is how many times the screen renders per second, is different depending on the device. For my monitor here and for the video, it's at 60 Hertz, which is just a fancy way of saying 60 times a second. Though on iPads and new phones with Apple's ProMotion technology, they might dynamically up this value to 80 Hertz or 120 Hertz. And who knows? There's certainly a limit of human perception, so it probably will never be 400 Hertz, but it could change for a variety of reasons. And so ideally, we could allow the device to let us know when it's about to re-render instead of guessing, and perform our physics calculations exactly then. And this is possible, and there are a few ways to link into this, but we're going to start with the simpler, hackier solution, just so we can get an idea of what's going on and incrementally step towards API nirvana. And so we're going to start by adding a little background to our view, sort of as just a hack, and we're going to construct this new timeline view, which came out a version or two ago. Takes two arguments. The first one is a timeline schedule, and one of these settings here is animation, and we're going to use that one. And then it takes a closure which accepts this context and returns a view. So we'll name that context, and for now I'll just put a little text field in here, hello, and we can see that the context contains a date, and we'll see here that it's printing out the full date, and it seems to be updating once a second, but that's only because the rendering of a date isn't going to show nanoseconds. If I say time interval since 1970, so-called epoch time, we'll see that it's jittering around like mad. If I make that monospaced, we can see that that number is just updating at a rapid pitch. It could be fun to figure out exactly how frequently this view is being updated, and we can do that rather simply. Up here, I'll make another piece of state called last date. We'll start it out with a date, and then I will say time delta, which I'll start out at 00, and then here, on change of our context's date, and what we could do is we could set the time delta equal to the context's date's time interval since the last date, and then we can set the last date equal to the context's date, and maybe we can render this as well, time delta, and here we see this peculiar double rendered to the screen, 0.016667 rendered, and that seems to be holding rather steady quite predictably. So this is the amount of time in seconds, a fraction of a second, between renders, the average time it takes between the calling of this callback in here. And if we divide 1 by this number, we'll see that it actually turns out it's about 60. What this means is this is being called about 60 times per second, and that's because, of course, on my Mac here, the refresh rate is around 60 Hertz, 60 times per second. So for now, we can use this technique to hackily perform some kind of computation, which we can put in here, compute in here, at the refresh rate of the device. So we will compute it just the right amount to have the smoothest animation without performing redundant computations. And now that we know this info, we actually don't need this text here. We can just say color.clear so that this is still being performed, but we don't need to see anything. And I can just show you that that is indeed the case by throwing text back here, though I do not have the context available, but we can still see the time delta exists. And that last date is still being updated 60 times a second. Okay. So now we've achieved a way of synchronizing some kind of computation with our device's refresh rate and getting the time delta since the last render, essentially. And that is useful because while it seemed to hold fairly consistently at 60 frames per second, there can be stutters occasionally. Maybe you're running some expensive background job. You open a bunch of tabs all at the same time. The computer might not render and decide to sacrifice the beauty, the buttery smoothness of animations in lieu of better computation performance elsewhere. So now that we can do this, let's actually compute some spring physics. In order to do this, I'm going to make a new class, actually. And I'm going to call this class spring double. We'll change this around eventually. And it's going to be a reference to some double value. And we're also going to store a target value, that equilibrium we are attempting to reach. We'll, of course, need an initializer. And we'll just have a simple initializer that sets the current value as the target. And then we're going to make a nice little animate to function that will take a new double and essentially just set our target to that value. And then in here, I'm going to have our custom offset spring equal to spring double of 200. And then let's jump down a bit and use this. So I will have our second circles view use offset spring dot value as its offset value. Inside of the tap gesture, I will similarly say offset spring animate to, and I will negate the current target. I'm negating the target here because the target will always be either 200 or negative 200, and this other internal value will be actually the presentation value that is shown on the screen. One last important thing to do is to jump up to the top here and import observation, the new observation framework, which I made a video on. If you would like to learn more about how that is implemented, I basically wrote it from scratch as well if you're into this whole scratchy thing. And now I'll scroll back down just a bit, and we're going to say @observable, add that attribute to our spring double class so that any changes to these values will cause the view to be rendered. And then what we're going to do is add one more function here called update, giving it a time delta. And basically in here, we want to perform the simulation. We want to update values somehow such that it approaches our target following all the laws of spring physics. Implement this all nice. We'll return here in a moment, but first let's actually call it. So now we can make use of our timeline animator and say offset spring update, and we can pass along our time delta. So now we're going to be calling update a whole bunch, though of course we don't see anything on the screen yet. If we want to prove that this is indeed working, we can just subtract some amount from our value, and we'll see that our ball is starting to levitate into the air and off the screen for all eternity. Goodbye. Maybe I can do this by the time delta multiplied by some amount. And now it looks even smoother. Okay, so we've proven that we can animate our ball manually, but now let's make this nicer. Let's recall a few of the terms we learned in that little physics lesson from before. The first important term was displacement, and that was the distance, the difference between our target and our current position. And if we want to have some fun, we can already set our value to be equal to its previous position minus its displacement, sort of undoing its displacement, if you will. And then when we click, it will animate once again between these positions. And if we wanted to, we could take Zeno's paradox and turn it into an easing strategy by moving halfway towards our destination every tick. And now if I click here, we'll see it is sort of animating in a really, really jumpy fashion. So we're not obeying the laws of physics here. It doesn't feel too great. But if I play with this factor here, this coefficient, it actually kind of feels a little bit like a really strong spring, but it's not quite delicate enough. So let's keep stealing from the universe and using physics. All right, so we have displacement. What were some of the other terms? I'm going to list them. There was the spring force. Maybe we could just set this as a variable. What was the spring force again? Well, Hooke's law told us that the spring force is equal to the displacement times some stiffness value. That stiffness value representing how strong the spring is, how much it seeks to undo the displacement. Of course, I don't have a stiffness value here, and it can be difficult to figure out a value that looks good given the constraints of our system. So what we're going to do is steal, not from the universe this time, but from SwiftUI itself. SwiftUI recently made a spring type that actually exposes some of these properties. So I'm just going to grab the default spring's stiffness, and the default spring is that critically damped spring. So we'll use this one. This is a double. And there's that other force, of course, which is the damping force. And the damping force resisted our velocity. It pushed against our velocity and was configured by some damping knob. Now, two problems here. One is that we don't have damping, but I will similarly steal this from the default spring. The other bigger problem is that we have no velocity. And velocity isn't something that we can just calculate out of thin air. It's sort of a property of the object in motion, and it's going to be changing over time as our object is subjected to acceleration and these other forces. So we're going to want to store this as well as a mutable value on our class here, and I'll say velocity is a double, and we'll start it out at 0. We'll start out not moving, though it will be very nice to have access to this field. If you watch the swipe actions from scratch videos, we can make use of setting the velocity to have a really nice animation in response to a gesture. But okay, now we have these two forces, and if we recall from the lecture, we want to combine them into some resultant force, essentially adding them together to figure out what is the actual force that will be acting upon our object. So that's great. We've calculated this force. We're almost there. So now the question is, how do we use this force to affect the position of our object? At the end of the day, we want to change our current position somehow, our current value, and actually we can sort of work back from the end. We can burn the candle at both ends, starting at the forces at one side, and then the other side, we know actually that the value will change according to the velocity. The definition of velocity is how the position changes over time. And speaking of over time, we're going to want to multiply this by that time delta. So our position is going to change at its rate of velocity. And because this is only going to be called once every so often, and that exact amount of time might shift dependent on the battery powers of our phone, etc., we're going to want to scale this velocity by the elapsed time since we've last simulated this physical snapshot. And that will allow for a nice smooth seeming animation over time, because otherwise we would be assuming that this update method is called at some fixed interval when that might not be the case. So we want to scale the effects of calling this method appropriately, which is what that time delta variable allows us to do. So this is where we end. This is where we begin with some forces, but now the question mark is in between. So step 1, question marks profit, and here is where we're going to want to change our velocity, which started at 0 and will remain at 0 unless we shift it around. And to understand how quickly our velocity changes, well, that's sort of the definition of acceleration. Acceleration is a measure of how speed or velocity changes over time. So if we knew our acceleration, we could simply update our velocity with that acceleration, similarly multiplied by the time delta. And so the last question is, how do we figure out acceleration? Well, you might remember from high school physics, I don't remember much from that class, but I do remember force equals mass times acceleration, FEMA. I'm not sure if I have all the capitalization correct here. And just like any equation, you can jump things around a little bit. So if we want to isolate the a here, we can instead divide both halves by m, which is the mass, and then flip this around and say acceleration is equal to force divided by mass. And for now, to make this super simple, we don't actually have to track mass. Most of the time in SwiftUI, mass is assumed to be 1. It's another one of those knobs that you have along with stiffness and damping, which can affect your animation, but I'm pretty sure usually it's set to 1, and shifting that around tends to make things move just too slowly or too quickly. So for now, I'm going to ignore it. We can bring it back later if we so choose. But with this done, our formula is quite trivial. Acceleration is force. Force is acceleration. Finkel is Einhorn, if mass is assumed to be 1. And so here I could just say acceleration is equal to the resultant force. A trivial aliasing, but I'll keep this here just so we can keep the physics in mind. And that was a bit of typing without testing anything. So let's actually click. And lo and behold, it looks pretty damn good. There are going to be some minor differences just based on the fact that we're using this somewhat hacky timeline animator. And there's also this sort of fascinating thing that happens if I wait and then click. The built-in SwiftUI animation seems to take a moment to start. Once it has started though, they sync up rather nicely, so I don't really know what's going on. It seems a bit slower to start. That might be some internal implementation detail. Perhaps it's trying to blend different animations together, or Apple just thinks it's nice to have a bit of extra oomph or delay in that first animation. I really don't know what's happening, but we don't really need it. And I don't know which one you think looks nicer. I kind of like the fact that the one on the right always animates the same instead of having a strange delay the first time. If anyone knows or has a theory, please comment and let me know. Other than that, hey, round 1 is done. We have implemented a spring physics simulator. Of course, this is where I tell you that there's still a ways to go if we want to make this nice. But let us take a moment to celebrate.
Next time on Spring Animation from Scratch, will our intrepid screencaster complete his prized API? Or shall he be thwarted once more by the pernicious forces of bike shedding, or spending time with loved ones? Tune back in next week for vector arithmetic protocols, display link rendering, and other fancy Swifty things. Goodbye!